Hey, what's up, Chem Peeps? Who is ready for some free response practice? A student took a 10.0 milliliter sample of acetic acid of unknown concentration from a stock solution provided by her instructor and placed it in an Erlenmeyer flask. The acetic acid solution was then titrated with 0.250 molar sodium hydroxide. The pH was measured throughout the titration, and the equivalence point was reached when 40.0 milliliters of the sodium hydroxide solution had been added. The data from the titration are recorded in the table below. Boom! Part A. Explain how the data in the table above provide evidence that acetic acid is a weak acid rather than a strong acid. Well, let's take a minute, peruse the data in the table. We are told that the equivalence point occurs when 40 mils of the sodium hydroxide is added. As I check out my data table, the pH at the equivalence point is 9.02. Interesting. I know that sodium hydroxide is a strong acid. If acetic acid were also a strong acid, the pH would be 7. I would have created a neutral salt. But because the pH at the equivalence point is greater than 7, that indicates the formation of a basic salt and that my acid was weak. According to the data, at the equivalence point, the pH is greater than 7. This indicates that acetic acid is a weak acid. Boom. 1 point. Part B. Write the balanced equation for the reaction that occurs when the solution of sodium hydroxide is added to the solution of acetic acid. Easy. Sodium hydroxide. Boom. Added to acetic acid. Boom. We're gonna form water. Boom. And a salt. In this case, sodium acetate. Boom. So, just like all our previous exams, your nomenclature is never going away. So make sure you practice it. Once I've gotten the formulas for each of my reactants and products, I'm going to go back and check and make sure this equation is balanced. Lucky for me, it is. Part C. Using the data provided. Subpart I. Calculate the number of moles of acetic acid that were in the 10.0 milliliter sample. Alright, let me go back up and take a gander at the data. I know that I'm working with a 10.0 milliliter sample of acetic acid, but I don't know the concentration. So how am I going to figure out the number of moles? Well, remember, with the titration, we are slowly adding a titrant of known concentration, in this case 0.250 molar sodium hydroxide. And it took 40.0 milliliters for us to reach the equivalence point. Or at that point, we will have reacted all of the acid. So, first thing I'm going to do, remind myself of the molarity formula. Boom. I do know the concentration of the sodium hydroxide. And I do know the volume in liters that I had to add to reach the equivalence point. A quick jump to the calculator lets me know that I added 0.0100 moles of sodium hydroxide to completely react all of the acetic acid. And thanks to that handy dandy equation that I just wrote up in part B, I know that the mole ratio between sodium hydroxide and acetic acid is 1:1. So since I know how many moles of sodium hydroxide I reacted, I also know how many moles of acetic acid I had in my original 10 mils. So my next step, bust out a stoichiometry calculation. Boom. Again, as you think about where this relationship between sodium hydroxide and acetic acid will come from, turn to your handy dandy balanced equation that you just completed up in part B. 1:1. 1:1. Which means that I must have had 0.0100 moles of acetic acid in my original container. Boom. 1 point for calculating moles from the concentration and volume, and a second point for showing that dimensional analysis. Even though it's 1:1, you gotta show your work. Subpart II. Calculate the concentration of the acetic acid stock solution. Again, concentration, we're coming back to molarity. Boom. I know from subpart I and my original question prompt that my 10 milliliters of acetic acid, or 0.0100 liters, contained 0.0100 moles of acetic acid. I don't even need a calculator for this. That tells me that the concentration is 1.00 molar for my acetic acid stock solution. Boom. Again, this is often the point of a titration. We're using a titrant of known concentration to determine the concentration of an analyte, in this case, acetic acid. The power of stoichiometry. Solution stoichiometry. Getting my solutions from my stoichiometry. Part D. Using the data provided. Subpart I. Calculate the number of moles of excess sodium hydroxide in solution after 50.0 milliliters have been added to the Erlenmeyer flask. Once again, I'm going to turn to my trusty molarity equation. I know that the concentration of my sodium hydroxide solution is 0.250 molar. I'm going to think about how many moles of sodium hydroxide I added after putting in 50 milliliters or 0.0500 liters of that solution. Quick jump to the calculator. 0.250 After adding 50 milliliters of a 0.250 molar sodium hydroxide solution, I've added 0.0125 moles of sodium hydroxide. So much was added. Now read this question carefully. We want to know the number of moles of excess sodium hydroxide after that 50 mils have been added. What you have to remember, back up here in part C, is that some of that sodium hydroxide that we just added was used to neutralize the acetic acid. Now, how much was used to neutralize the acetic acid? Such a good question. The amount needed to neutralize the acetic acid is the amount that we added up until the equivalence point, which we calculated to be 0.0100 moles. So, if I added 0.0125 moles of sodium hydroxide after dumping in 50 milliliters and 0.0100 moles of sodium hydroxide reacted with the acetic acid, that means, I don't even need a calculator here, 0.0025 moles of sodium hydroxide are in excess. Boom. That brings us finally to subpart II. Calculate the pH of the solution in the Erlenmeyer flask after 50.0 milliliters of sodium hydroxide has been added. All right, well, at this point, think about what's in solution. There's no more acetic acid because we completely reacted it all with the sodium hydroxide. But there is 0.0025 moles of sodium hydroxide still floating around in excess in our flask. And that's the thing that's going to contribute to the pH of our solution. So, once again, my good friend molarity. I know that floating around in solution, I've got 0.0025 moles of sodium hydroxide. And here's the tricky part. That 0.0025 moles is floating around in a total of 60 milliliters of solution. Why 60? Well, recall that initially we started with 10 milliliters of our acetic acid. And at this point, we've added 50 milliliters to that 10 milliliters. So our total volume, 0.0100 liters plus 0.0500 liters. Or, simplified, that excess 0.0025 moles is floating around in 60 mils of solution. Jump to our calculator. The concentration of our sodium hydroxide solution is 0.042 molar. All right. That is the concentration of the sodium hydroxide solution. We're trying to determine the pH, but because I'm working with excess base, I know the concentration of my hydroxide ion. My next step, determine the pOH of this solution. pOH is equal to the negative log of the hydroxide ion concentration. Now, the reason I'm doing this is because I'm working with a sodium hydroxide solution. Even though I'm looking for the pH, the only way I can get there is by first solving for the pOH. Now, I know the hydroxide ion concentration is 0.042 molar. And I know that because sodium hydroxide is a strong base. And the ratio of sodium hydroxide to hydroxide is 1:1. So a quick jump to my calculator. My pOH is 1.380. Finally, recall the relationship between pH and pOH, that when you sum them together, you'll get the value 14. We're looking for the pH. We know the pOH is 1.380. Simply going to subtract my pOH from 14. 14 minus pH equals 12.620. Boom. Free response done.